Hey guys, welcome back to another video, and today we'll be discussing about the Bellman Ford algorithm. So this algorithm is responsible for finding out the shortest path from a single source vertex to all the other vertices in a weighted graph. So this is similar to Prims and Kruskal, the algorithms that we did in like the previous videos, but in this case in Bellman Ford we can work for negative edges. So we'll be looking into that in as we go on in the video. So the algorithm is this one, and I've written down the time complexity. So to get to know more about the time complexity, you can look up the Wikipedia page or something else. So the algorithm is, so let me go through the algorithm first. This is a very simple algorithm. So the first portion, this for loop, is responsible for initializing all the values. So we haven't traversed the whole thing yet, right? So that's why everything is initially infinity, and the parents are null. And so next up we have to like define who's going to be the starting node, because we need to start from somewhere. And the next for loop, this would go from like 1 to vertex minus 1. So in this case we have 5 vertexes, so it would go for 4 loops. So this is responsible for finding the adjacent nodes of each vertex and updating the parents and the distance. And what expand / relax function does is like it says that this particular vertex has how many edges or how many vertices adjacent to it. The final loop, this one, this would run only one times, and it will only check if there are any changes to this table even after the first four loops are already done. So rather than talking about the whole algorithm, let's try to go through the simulation and see what happens. Okay, so S would be our starting node, right? So as the algorithm says, so the distance would be 0 at first. So this is 0, and the parent is null because the roots, this is the root node, and root nodes don't have any parents to begin with. Okay, so from S we can go to 2 places, right? We can go to A and we can go to C. So let's try to update the values. So 5 is of course much smaller than infinity, so it would be 5, and the parent is S. And we can go to C, so the C is -2 and the parent is S. Okay, so we are trying to go alphabetically. So from S we would go to A. So we have like visited S one time. Now we're gonna go to A. So from A we can go to only one place, that would be B. So 5, we already have 5 plus 1, that would be 6. So this is 6, and the parent is A. Now from B we can go to 2 places, right? So we can go to C and we can go to D. So that will be 6 plus 2, that would be 8. But C already has something much smaller than 8, right? It already has -2, so we don't need to update this. And we can go to D, so that would be 6 plus 7, that would be 13. And the parent would be of course B. Okay, so we are done with all the adjacent of B. Now coming back to C. So from C we can go to 2 places, that would be A, and another one would be D. So C we can go to A, so it would be -2 and 2, so that would be 0. So 0 is much smaller than 5, right? So we update this, and the parent is C. And we can go to D, so -2 plus 3, that would be 1, so which is of course much smaller than what we had. So we're done with C2. So we go back to D. So from D we don't have any other outward edges, so we're done with D. Okay, so we go back to the loop again, and as I said before, that it would run 4 times. So I've gone through the whole thing one time, and let's go through this another time. And I'm not gonna go through all the 4 loops. you would know why just in a bit. So let's go through it again. And from S we can go to two places, which is from A, which is 5, but A already has a smaller value. And we can go to C. C already has -2, so nothing needs to be updated. So from A we can go to B. So A has 0, so 0 plus 1, that would be 1, which is much smaller, so we update it. Okay, so and we can't go anywhere else from A. So from B and go to C. So 0, we had 1 and 2, that would be 3, but C already has something much smaller, right? And we can go to D. So 1 plus 7, so that would be 8, but D already has a much smaller value, which is 1, so nothing needs to be updated. And we have C, but as I said before, nothing needs to be updated here. So we are done with A and we're done with B. Now we're coming to C. So from C we can go to A. So -2 and 2, that would be 0, we already have that. And from D, that would be -2 and 3, that would be 1, we already have that, right? So we're done with C. And D doesn't have any outward edges, so nothing with D. So this whole thing is going to be going for another 2 more loops, right? And from the graph you can understand that nothing is going to be changing anymore. So we are all done with this portion where nothing changes, and we are already updated everything in the table, right? And in the next loop, in this one, we'll be going through this one more time, and we are not gonna see any changes. So that means this whole thing, the whole graph, doesn't have any negative edges. So as I said in the algorithm, if there aren't any changes, so that means there aren't any negative cycles. So that's about it. So this constructs the whole Bellman Ford table, and we know all distances and parents. So I made a mistake here, which is that the parent wouldn't be B. That isn't possible. So the only thing is going to be A, because we come to B from A with the distance of 1. Okay, so let's try to look at how the minimum spanning tree is generated. So we start from S, which is our starting node, and from S we go to C. From C we can go to A, and we can go to D, and we can go to B via A. So yeah, that's about it. So this is the whole minimum spanning tree, and this is the path that we should take to reach any one of the nodes. And hope you guys did understand the whole concept of Bellman Ford. And if you have any questions or suggestions on what videos I should make next, please write them down in the comments below. Thank you.